that noise really is a very important topic, but it's one I don't know if this was Baader-Meinhof syndrome, the idea that whilst you're thinking about something, it appears more often. Because certainly when I was doing my doctorate on this subject, there seemed to be a lot more people dealing with noise. And like I say, I don't know if this is just my view of the world, but there does seem to be a lot less people now considering what noise could do for their system. It certainly was a subject that came around at the beginning of my doctorate because computers were just getting fast enough that you could run 1,000 simulations and gain, the statistics, over those 1,000 simulations. Whereas previously, running one simulation took long enough, but we were getting into that sort of high power computing era. But so how did I get into this? I didn't do noise. My undergraduate was through Oxford, and we did deterministic systems. The only discrete stuff we did was really recursion relations. So when it came to my doctoral interview, they said to me, okay, what do you want to do for your doctorate? And I said, oh, Turing patterns. I love working with Turing patterns. They're beautiful, theoretically, simulation, incredible things. Great. Would you do them with noise? And I remember sitting there for a moment going, no, I wouldn't, because I don't know how to. We're not taught how to deal with noise, so why would I do that? They said, fine. I got the position, even though I'd said no. And then on the first day, my doctoral project was putting noise in Turing patterns. So fair enough. By the end of it, at least I have now a respect and an understanding of what noise can do for us. So let's get into what the whole subject's about. Power of noise, weak noise, and power spectrum methods. We're going to look a bit more at the weak noise. When I was collapsing all of this down, didn't really have too much time to put the power spectrum methods in. So I will mention them, but it's really the weak noise aspect that we're going to cover in the next 20 minutes. Oh, and if you do have any questions, please do shout out, wave your hand, whatever you need to do, get my attention. Questions throughout, please. Oh, Turing patterns. Turing patterns. We will talk about Turing patterns. If you don't know what a Turing pattern is, don't worry. I can talk for days on Turing patterns. They're absolutely wonderful. And in fact, my second slide is a Turing pattern. But before we get there, let's talk about noise. What do I mean by noise? Because there are many, there's two broad branches of what noise could be. There is intrinsic noise and extrinsic noise. And within those, you can break it down to finer grains. But they're my two branches that I'm going to talk about. Intrinsic noise is, as the name suggests, noise that arises from the system itself. So mainly I would think about small finite particle systems. The idea is that these populations have a small number of individuals, 10, 100. What does small mean? It's a comparative idea. So small number of interacting components, and their interactions occur stochastically. So the idea of what a chemical reaction is that two particles come along, they hit each other with enough energy to get over their energy barrier, and the reaction fires. That's intrinsic noise. Extrinsic noise is then whatever I do to the system. So imagine, rolling of the dice. The dice roll itself is intrinsically stochastic. But then suppose I roll my die into a box and I'm shaking that box. That's extrinsic stochasticity, because if I shake my box with a high enough amplitude, my dice will never come to rest. They'll be bouncing around. So you have these two ends of what stochasticity can mean. But I'm going to primarily focus in this talk on the intrinsic version. And what does that mean? The idea is that let's consider a reaction. A plus B goes to C. I have two populations, A and B. They interact, and they produce a population C at the end. I can write down ODEs for that means using the law of mass action. And for argument's sake, let me use a rate of 1/6. If I simulate that with a rate of 1/6, then every 6 seconds, I will get a population C. Every 6 seconds, A plus B react to give me C. Deterministically, every 6 seconds, C is produced. I can alter that definition to be about dice rolls, stochastic. So I'm going to say A and B react with each other whenever I roll a 1 on my die. Standard die, I roll my die every second, and whenever I roll a 1, A and B are said to have reacted. So I roll my die, roll my die, roll my die. Over any short space of runs, I might get a few more 1s. I might get a few less than 1/6. But over a long enough period of dice rolls, I will get back to that rate of 1/6. Okay, so that's the idea of where this noise is coming from. It's the stochasticity of the interacting particles. And that's what's right down at the bottom here. This, I think you can see my point here. So right down at the bottom here, we write down the probability that every individual reaction will fire. We take what's most likely to happen, and then it fires. From that, we get the chemical master equation. That's the CME. We'll talk about that in a few moments. The chemical master equation, high definition, high dimension, quite nonlinear, very difficult to work with. So we often have to simulate it. And so we use the stochastic simulation algorithm. The stochastic simulation algorithm is an accurate simulation in that if you simulate enough of them, on average, you will converge to the distribution of the chemical master equation. So sometimes you can't solve the chemical master equation analytically, but you can solve it through simulating thousands upon thousands of simulations and then averaging over them. All of that is exact in the sense that you'll get every individual reaction firing, you'll follow every trajectory of every particle. From there, you can start making approximations which make your simulations faster. So if you have a large-ish number of particles and the population doesn't change very quickly, you can, instead of updating every single interaction, you can update after every 10 reactions, after every 20 reactions, something like that. That gets us to something called the tau leaping. And all it is an approximation that your population isn't changing that much. So instead of updating every interaction, I update after every 10, every 20. So it speeds you up a bit. From there, if we then say we've actually got quite a lot of particles, we don't want to simulate every single one because that will slow us down. So we can then scale things up, and what we get is the chemical Fokker-Planck equation or the chemical Langevin equation. Two equations, they make your populations continuous, but they keep a feeling of noise. The noise is scaled such that it's doing what the lower levels would be doing if we simulated lots and lots and lots of particles there. And finally, if we make our populations practically infinite, the stochasticity disappears, and we get down to the reaction rate equations, which are both continuous and deterministic. So at that point, we've lost what the noise is doing, but we're going to be staying around this level here, the chemical master equation and stochastic simulation algorithm. If you want more information about that, go see this paper by Dan Gillespie. Dan Gillespie was one of the people who, at the forefront of this, he was one of the people behind the stochastic simulation algorithm. Many people called it the Gillespie algorithm, but his terminology was SSA. Wonderful review, really beautiful. It gives, I think this paper here comes with code and things. So it's actually a really, really good starting point for anyone wanting to get into how do I simulate a stochastic equation. So for those who don't know about Turing patterns, here is the be all and end all of my existence. A Turing pattern is a reaction diffusion system. It has two parts, reaction and diffusion, such that each part on their own do not pattern. The reactions are stable. If you simulated them as an ODE, they would do nothing. They would just go to steady state. Diffusion wipes out patterning. Oh, I think I had another question. Oh, yep. Thank you, Maria, for putting that in the chat. The diffusion tends to wipe patterns out. You know, if you put ink in water, the ink diffuses out and spreads out, and over time you'll get blue water. You don't get spots of blue. You don't get stripes. The diffusion wipes you out. But the genius of Turing was that he showed that if you couple diffusion and the reactions together in the right way, the diffusion can actually drive your system to instability. Insane idea. Took 30 years before people really understood what was going on. You know, he was really a genius ahead of his time. But now we're very comfortable playing around with them. And that's what you're seeing here. This is actually a Turing system on a growing domain. So if I just freeze one time section, that would be a 1D domain, and I would have a peak of activator. You know, what you're seeing here is the yellow is where let me draw a graph of what that 1D slice would look like. We would have a low region, we'd have a high region in the middle, and then we'd have a low region again. This will be some population U, and this would be the space X. Okay. What I'm doing on here is I'm growing the domain. Okay, so I'm stretching uniformly. This interaction is occurring on a rubber band. I stretch my rubber band, the whole thing grows, and I'm growing exponentially. And what was shown a few years before I did my doctorate, beautiful piece of work by Edmund Crampin. He showed that if you grow reaction diffusion equations on an exponentially growing domain, you get pattern doubling. You start out with 1 peak, you get 2 peaks, 4 peaks, 8 peaks, 16 peaks, and so on. You keep growing, you keep doubling. But this is only true if everything is deterministic. What happens when you add noise? Let me clear my drawings and go to that. Everything breaks down. Well, not everything. You still get patterns. So patterns are still there, good start. But you no longer generate the period doubling that Edmund saw. Okay? Can we understand this? And this was my doctoral question. What is the noise doing? Can we stop it? Can we stop it breaking down? Because sometimes we want Turing patterns to have this robust feature of creating this doubling cascade. Other times we don't care. If you want to talk about zebra stripes, you want all your zebras to be unique. But if you're trying to use Turing patterns to understand your finger placement, you want to be able to always end up with 5 fingers. You don't want to end up with 6, 6.5, 7, 2. You want a robust mechanism producing these patterns. Okay, so let's get to some noise. To write down a chemical mass, let's start with deterministic. Many people are familiar with the deterministic. When you write down ODEs or PDEs, you're writing down fluxes. You're saying I'm in a state U, and this is a source that will bring my system into state U, and these are the sinks that will take me out of state U. If I have a population increasing, it will increase my population. If I have a population dying out, it will die out at certain rates. The chemical master equation is very similar. You're still writing those fluxes in and out of a state, but you can no longer say what state you're exactly in. So instead of saying this is the rate coming into U and this is the rate going out of a state, we have to say, well, what is the probability of jumping into state U? And what is the probability of jumping out? But otherwise, it's exactly the same. But in other ways, it's completely different. Here's the chemical master equation. The left-hand side is the rate of change of the population of the state U. We normally suppress the U0, T0. That's just saying we're starting at T0 with initial condition 0. This is equal to then the summation of all the interactions that could bring us into state U. So we're one reaction away. We want to be in state U. We're actually in U minus nu. Okay, so if we're in U minus nu and the U minus nu equation fires, we'll move into state U. And then we subtract out all the probabilities that we jump out. So we are in state U, a reaction occurs, that removes us out. Okay, otherwise, it's just this idea of what puts me into the state, what moves me out. We can no longer say we're definitely in the state, so we work with probabilities. Let me give you a concrete example, logistic growth. Hopefully, you're all very familiar. It's this idea that a population will grow, but binary competition will keep it finite. Here's how we would write it down. To get into the population state U, if we start one away, and there are K1, U minus 1 times that we could grow one more person. So if U is population, the probability of the reaction firing is K1 times U minus 1, because we're in the U minus 1th state. Once that fires, we go from U minus 1, we gain that extra person, and we go to U. So that's the rate of moving into state U. If we're in state U and this reaction fires, K1 times U, probability rate of it firing, that will move us out. So we'll be in state U, we'll gain one more person, and we'll be in state U plus 1. The backwards reaction is the death reaction. So we are in a state of U plus 1. We have a probability of, it's a binary interaction now. So the U particles can interact with the U plus 1 particles. The rate K minus 1 tells us how likely it is to happen. And one of those particles dies out. So we go from a population state of U+1 to a population state of U. That moves us in. So that's why it's a positive. But again, if we're in the state U and the binary interaction occurs, we move out of the state U to U-1, and that's why we have the negative. Okay. As I say, this is quite hard to deal with. We can actually deal with one. It's not too bad. This is only a quadratic nonlinearity here. It's nasty enough. But as I say, instead of solving it, what we can do is simulate it. So what we're saying here is this black line would be the deterministic solution. If I wrote this, instead of writing down the chemical mass equation, I used the law of mass action to write down the ODE system. I solved that. That's what the black line would give me. Population would increase up to whatever. I picked some parameters here, and I've got a population of 100. However, if I simulate this stochastically, this idea of I roll the die, and do I grow or do I decay? Well, that's based on these probabilities here. And we get this blue stochastic trace. Again, it follows pretty well. It increases up, and then it grows a little bit more or a little bit less, but it's bouncing around this population of 100. Okay, so that hopefully gives you an idea of how this all fits together, how you can use it to describe a stochastic system. That's an ODE. We want to deal with space. So how are we going to deal with that? I'm going to discretize my space. So I have one dimension. I'm only doing this in one dimension. You can do it in higher dimensions, but growth becomes problematic. Similar, sorry, there was two questions there. Similar to Smolny-Chomsky's equation, detailed balance. Pretty much. You can look at it. Smolny-Chomsky's equation is an equivalent way of formulating it. So yes, you can certainly use detailed balance arguments. I take my space, I chop it up into k boxes, and each of these boxes now has an index. In this box is U1, U2, U3, all the way up to UK. And I create 2 K reactions. K to move me to the left, and K to move me to the right. Each have the same probability. The only reason why one box would move more is that it has more particles. So this is what the definition of diffusion is. Every particle in box 1 has a probability of jumping D to the right. Every particle in box 2 has a probability of D jumping to the left, D jumping to the right. If there are more particles in the second box, then it's more likely that one of those is going to jump than those in box 1. So yeah, we say all the probabilities are the same. Every particle has the same probability of jumping. It's just if you have more particles, then you're probably going to have one of those jump rather than one of the others. So I don't really want to get too much bogged down into this, but here's the chemical mass equation for this diffusion. We have K jumps to the right. We have K jumps to the left. Actually, K minus 1 because of the boundary condition. We're going to have Neumann boundary condition. So everything can jump around in my 1D system, but we can't jump out. You can make your boundary conditions do whatever you like, and it would all fit into this framework. So let's now simulate diffusion. On the left and on the right, we have essentially the same simulation, at least deterministically. So again, we've got this red line here. This is the deterministic solution to diffusion. I put a load of particles in my left box. I let them diffuse out. In the left-hand simulation, I have 1,000 particles. In the right-hand population, I have 1,000,000 particles. That's the only difference between these two. And you can see all the difference that makes. It's still noisy. You can just about, if you look closely, you can see that there's a blue line underneath this one that's doing stochastic bouncing around. It's easier to see, of course, in the left because there are less particles there. And this is the key idea that will help us do a weak. Oh, I have a question. Consider delays. You can consider delays. There's a lovely piece of software out there called Dizzy, named after Dizzy Gillespie because it was called a Gillespie simulation. And you can put delays into this. If I have time, I'll talk about a bit more about that at the end. Essentially, delays ruin everything. But we'll talk about that a bit more at the end. So as I say, this is the key idea that will give us the weak noise expansion. As you increase the number of particles in your system looks more deterministic. The absolute value of the noise increases, but the relative value decreases. So there is still noise there, but we're going to be looking mainly on this idea of the system, that we've got a lot of particles in our system, a few thousand, such that it is stochastic still, but it looks deterministic. When you have stronger noise in the system, things get a lot more complicated. There are still techniques out there, but we're going to deal with weak noise. So we have our chemical mass equation on the top here, and we're going to use exactly this idea that my stochastic population looks deterministic. Phi is going to be my deterministic solution. So if you were to simulate ODs or PDs that you would write down normally, that's what phi would be the solution to. Plus a noise term, eta. And this is all scaled by the population size omega. So if I divide through by omega and send omega to infinity, I'm at the thermodynamic limit. I get back to my concentrations, they're deterministic. So what I really want to know is, what is my noise doing? Because it's now has a square root omega. How do I justify this? This is an ansatz. I'm throwing it in, and it's justified a little bit by the law of large numbers, the central limit theorem. The idea, if you have a large number of simulations, it looks Gaussian with population mean of what you would expect and standard deviation square root size of the population. So that's the idea that we're using. It doesn't have to work, but generally it does pretty well if you have a large population. So what I'm going to do is I know phi. Phi is ODs and PDs theory. We can do that. Eta is my noise. That's what I really want to try and understand. So I write my U in terms of eta, and it's pi. I rewrite everything in terms of pi, and that's what I really want to understand, my stochastic distribution. I'm going to zoom over a lot of theory here. It just gets a lot of algebraic detail. Let's go back to our logistic example case. The ODE that you would write down, very simple, K1 times phi minus K1 minus 1 phi squared. You have to account for the population size omega in there. That's the ODE. We substitute in the omegas. We then expand in terms of those omegas. The first order will be the ODE system. The second order is then this pi. This is called a Fokker-Planck equation. And this tells us what happens to that pi function that controls the noise. One thing we're also going to do is we're going to simplify things. We're going to throw out the time derivative. We're going to say what happens at steady state. If things are at steady state, we can solve this. We can say that that's 0. So we can solve for phi, put phi into here, into here. It just becomes then a second order ODE, constant coefficients. We can deal with that. It just becomes a Gaussian. So here's the solution. Here's the steady state. There's the equation we have to solve. Here's the Gaussian that you end up with. So here's the simulation that we had originally. That's following one trajectory. What this is saying is that if we followed thousands of trajectories, the noise should follow this distribution. And this is what we're going to see in this picture here. The red curve is this pi function. And beneath it, this blue histogram is me running thousands of simulations, running it to time 100, and then boxing the tallying up where is my population at time 100. And this is where that population was. And as you can see, it does pretty well. We underestimate a little bit on the right-hand side. We overestimate a little bit on the left. But overall, we did pretty well. And this is with a few hundred particles. You don't need that many particles for the weak noise method to work. Now, I can see my time is running away. So let me give an overview. You can do this on spatial systems. It just becomes more algebra. And my key aspect was, can we understand what modes what modes, what spatial frequencies is the noise amplifying? Because it's still producing patterns. We can see that we're producing pattern. That's not the hard thing. But can we understand what spatial frequencies is the noise generating, activating? And yes, we can. Is a very shortcut answer. This is all of the power spectrum methods that I really don't have time to talk about. But what you can do is, from that Fokker-Planck equation, you take a Fourier transform of it, just like you would the PDE system, and that will tell you what frequencies the noise is activating. So this is what kind of graph you would get here. This is telling us that we would expect the frequencies noise to activate frequencies 2 and 3. So we have these two frequencies being activated. If you simulate the Turing system, then this is exactly what we get. So a mode 1 is half a peak. So as you can see here, we have a full peak. So this is a mode 2 pattern. 2 half peaks make a single peak. And over here we have 3 half peaks. So this is a mode 3 pattern. These are the kind of patterns you would see, and the noise is helping you produce them because it's amplifying these pattern formation systems. So this is one thing I want to touch on, is that the noise is actually helping. Many people think of noise as a destructive force. It muddies your data. But in the Turing system, it actually helps you pattern because it amplifies the spatial frequencies that you expect.
Can I ask a question?
Please do, please do.
Sorry, just when you say that amplifies spatial frequency, in my terms, could it also be like, because it allows you to move across space, a state space more, like it lets you explore a little bit more? Is that
that happens as well? So in Turing systems, deterministically, let's say you derive a parameter region here. When your parameters are within that region, you get Turing patterns. Once you're outside, you probably don't. What noise allows you to do, so out here, your system would tend to steady state exponentially slowly. So what the noise does actually kicks you out of this steady state. So your patterns can exist outside of the regions your deterministic system says they should. They still exist within here. Within here, you still get your Turing patterns, very nice, happy Turing patterns. Outside of that, you shouldn't. But the noise keeps pushing you out of that steady state. So the steady state is the thing that's unstable. And so you actually get patterns in a wider parameter region than you normally would. Did that answer your question, Maria?
Yeah, no, and I know, like, when you sort of opened up and said like noise in Turing, when you showed the Turing and everybody was afraid, like, why doesn't it do these like, repeated patterns? To me, maybe actually having the noise guarantees that you're going to be in those spaces a little bit more. I don't know. I'm just
very much so. That's next. So if you consider the bifurcation, this was a paper I just had published actually. So if we consider the Turing bifurcation, if we're in a Neumann system, it's a pitchfork. So here your system would look flat. So this is a parameter L, say, and this is what U looks like. Let me erase that because that looks rubbish. So if I have a parameter region here, then deterministically, I should get a flat space. So this is now a simulation where of population U over space X. If I'm now in this region here, my steady state becomes unstable. And what I see is that my system patterns. Okay, so that's what the bifurcation, pitchfork bifurcation, just says at this point here, my steady state becomes unstable. I go from the homogeneous system being stable to a pattern system being stable. Great. But the bifurcation diagram is a lot crazier than that if you go further. What you find is you get multiple peaks, things like this happening. And what previously happened is the system went from a mode 1 to a mode 2 to a mode 4. And so your system would follow this. It would go boink, fall onto there, and then boink, fall onto there in mode 4. And it would fall onto 8 and fall onto 16. The noise, as you say, allows you to, so the noise would, first move you along here. It would move you up to 1, but the noise would then push you onto 2. The noise is then likely to push you onto 3, the noise is then likely to push you on to 4, and then the noise is likely to put in. So you get a consecutive increasing rather than the nice clean doubling. Another way of seeing that is in the last slide. You've already seen this. This was on the uniformly growing domain. And as Maria said, what noise is doing is pushing you off one bifurcation branch onto a different one. Because you're growing uniformly, there's too much area. Area is appearing everywhere, so the peaks can appear everywhere. There's just too much noise in the system. So how do we get back to a system that robustly creates patterns? Instead of growing everywhere, grow apically. What do I mean by that? Grow just at one edge. Increase the number of boxes just at one edge, because you're controlling where the area can appear. You're controlling where the next pattern can appear. So you're controlling which pattern can then next appear. So in this simulation, what I'm doing is growing just along this edge. And what you see is I start with half a peak, I get 1. I get 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, etc. So if I just keep growing at one edge, I control where the next peak can appear. I can control when it next appears. If I don't want any more, I stop growing. So this is sort of a fundamental idea of what noise can do for us, what growth can do for us. If you don't care what your pattern looks like, if you're a zebra, grow uniformly, grow as much as you can, as quickly as you can. You'll get stripes everywhere. If you're trying to grow fingers in the right places, grow apically. And that's what's seen, or at least people where I've worked with, they have a limb bud, and the limb bud grows apically. And so you get this consecutive increase in the number of digits that can appear. So it makes it more robust in whatever pattern you want to generate. So just to skirt over the sort of main points that I want people to take away. Noise can be important. When is it? When isn't it? Hard to say. Certainly if you're dealing with a small number of components, you should be using stochasticity. It can change your system. It can change whatever the dynamics is doing completely. If you're dealing with a large number of particles far away from bifurcation points, you're probably okay. Noise is not necessarily destructive. This is what people mainly think. Noise is a bad thing. Doesn't have to be. Noise can kickstart you into something earlier. It can help you kickstart patterns where you wouldn't expect them. It can do a lot for you. And finally, analytical approximations, if that's what you should wish, can be generated. It's not just a simulate and hope. We can understand what the analysis is doing, at least in the weak noise regime, and they're usually pretty good. Each individual simulation will be noisy, stochastic. Perhaps we can't understand that single simulation, but as an ensemble, we can get an idea of what they will be doing on average. And with that, I thank you all very, very much for listening. Relate noise versus diffusion. That's a very good question. There's another question here about relating noise with diffusion. Diffusion is Brownian motion. It's the fundamental idea of a random walk. I've constrained my random walk to be on points. You know, I have my discrete boxes. There is another way of describing stochastic systems called the Smoluchowski equations, where you're not only considering the interactions, but you're considering the movements to be stochastic. So it's a whole nother level. There's, again, theory out there to deal with it. There are simulation packages out there, one called Smolden, Smoluchowski dynamics. What can I say about it? On the whole, for me, space wasn't that important. All I needed to do was get these patterns appearing. If you really need to follow particles moving over space, because one of the big things that it was used for was following protein flashes in C. elegans. Their location was really important. Where is this protein flashing? So that's why Smolden was used there. For me, not so important, so I don't need to go to that level, but if you need to know where your positions are, not only how many you have, then you should go to this Smoluchowski description as well. But otherwise, yes, questions, comments, thoughts, queries, please throw them at me.
So I'm still asking the same question.
Please do, please do.
First, you said that the noise may destroy or blur the pattern, and you showed it very well. But then the noise helps to reveal the pattern. So there is a bit of yin-yang here.
Very much so, very much so.
Effect of noise. And the question is, where do I put the finger?
So we have to ask, what is it destroying? It's not destroying the pattern. It's destroying the mechanism of robust pattern doubling. So if you think about this pattern doubling as following some bifurcation diagram, the noise is pushing you off branches that you normally wouldn't. So that's what it's destroying. It's destroying that mechanism. It's giving you patterning. It's amplifying the spatial frequencies that are already there deterministically. So it's helping you pattern. It just, you may not get the pattern that you want. That's the problem. So how do we get the pattern we want? Instead of growing uniformly, where, as I say, you're getting too much area everywhere, so pattern can appear everywhere, very, very noisy, very difficult to control, just grow at one edge, because then you're controlling that pattern appearance. So again, you can robustly generate any pattern you like.
Cool. So I missed, maybe you had to rush away with 25 minutes, but maybe you can elaborate on the spectral method, noise method, and the Turing pattern.
I would happily do that. Are there any other questions? I will happily, I've got another longer presentation here, which I can sort of go through some of the subtleties, but that does get dirty. It gets very mired in the algebra. So are there any other questions before I do that?
Sure, absolutely.
Well, I was going to just maybe push the discussion a little more because we're into the development and
Sure,
regeneration,
sure.
and I just thought that apical finding is pretty important, I guess, if you're thinking about a developmental system. So Itamar, is that okay if we just kind of discuss that before we, I think they're related too, but absolutely, I just wanted.
Absolutely, I'm just asking for the sake of asking, you know, curiosity.
No, I was just,
pure curiosity, no agenda, no research proposals.
No, it was just intriguing, right? So I just meant that, does it mean that we could start looking at sort of like repair or some sort of and seeing where the cells will have to, like, I have heard of, like, you know, if you cut off the finger, it's only the tip that seems to grow, but I don't know if it's just because that's where also the stem cells are located. Like, there's a lot of different elements about it, but I'm just wondering whether it was like a sort of a like developmental evolutionary drive that made.
I would think so. So the other case I know of is we work with some people in Edinburgh, and they work on mouse skins and various bird skins, so ducks, geese, the emu, ostrich. So for the mouse, you don't care where you place your hair follicles. You can place them wherever you like. The mouse grows uniformly during development. Ducks, chickens, flightful birds, they have to have very, very carefully placed feather buds, because you want to be able to fly, you need to be aerodynamic. So what you see is that although the skin grows, the hair follicles don't appear straight away. The feather follicles don't appear straight away. What happens is you have your skin form, then a priming wave appears from the central midline where the spine is, and the feather placodes fill in behind it. So although all the skin is already there, this priming wave acts like an apically growing domain because it can only fill in the feather buds behind this moving wave. So you get a regular formation of the feather patterns. So the other one, the ostrich, because this was a really cool project, we haven't published it yet, but what they showed was flightful birds like ducks, geese, chickens, very regular arrays of feather buds. Ostrich, emus, flightless birds. They don't care where they put them. Again, they place their feather buds anywhere. And again, there's no pattern forming wave. It just happens. You know, you don't need to be careful. Just put them in as you like.
Right. No, that's actually, but I was also thinking about more like a single cell, like a stem cell. And maybe there might be also a reason that we come down to, I mean, more than we don't want everything to be able to regenerate, but I wonder if we're able to simulate a region where you would probably have more than one of these stem cells being able to proliferate versus one, and that propagates the system. I wonder whether that if you have any intuition of whether that would give you more robustness, because I mean, that would be
Well, actually, it's rather the other way, kind of, because again, this kind of goes back to what I know about colonic crypt signaling, and when you get cancer, colon cancer, unfortunately. The idea there was, if you create a small number of mutations that generate clones of themselves, that this is what's causing the cancer, what happens? And what you find is generally you don't get a heterogeneous tumor. One of these populations wins out, and that becomes the cancer. And one thing what you want to do with cancers is keep heterogeneity, because if you have a heterogeneous population of cells, some of them will be weaker than others. They'll all be using energy, nutrients, but you'll be able to kill the weaker ones. And this is why, one of the problems with cancer at the moment is that once you've killed off all the weak ones, the strong ones find room to multiply, they develop, and you get single strands of stronger cancer cells that are that stop being weakened to drugs or immunotherapies. So that's why you want tumors to be heterogeneous. You want to keep that weakness built in.
True. I mean, I could see where you'd have to balance the two. So
there's a whole, people in oncology, there's a whole field of this now saying, actually, you might not want to remove the whole tumor, because if you blast it with radiation and you wipe out 99%, you may think great, but that 1% is your problem, because that's what's going to grow back.
I think there was a hand up. Shibashi.
Was that right?
Yeah. Hi, it was a nice talk.
Thank you.
Yeah. So my question is, I actually, during my doctoral days, I actually worked with some noise like dichotomous noise. And I have found that when I apply the noise additively, the system actually doesn't respond that much. But when I use the noise multiplicatively, the system actually patterns. So is there any, I actually didn't continue the project because of this anomaly. So is there any this explanation for that?
So fundamentally, I don't know, because that's the external noise. If you're choosing where to put your noise term, you're shaking your system in a specific way.
Yeah.
That's sort of outside my I know bits, and I'm just going to try and find. There's a really great book. I'll just try and find it for you. And it covers all this idea of, if you add the noise, this is what analytical techniques you can use. If you do a multiplicative noise, this is what you can do. Let me just get it for you. Garcia Halvo. Colored noise and spatially extended systems. Oh, that's a paper. So I mean, hopefully that will be a good. I'll put this in the chat. This will be a good place to start. Well, essentially anything by Garcia Halvo is really good. But where's the the book is also called Noise and Spatially Extended Systems. Really good book. If that's what you want to know, have a look at that book. That covers everything from the very basics all the way to the more extended ideas.
Okay, thanks.
Oh, let me come back to one of the questions though about delays. So we did look at delays in this system as well. And because delays screw up Turing patterns royally, which is problematic because it takes time for proteins to be produced. And some delays can be quite hefty, 24 hours, 48 hours. So how is it, when we simulate things, we assume there's a load of A and a load of B and they react. That's sometimes not how biology works. Biology produces A at a low rate. If you do that, if you put that delay in, Turing patterns disappear. If you add noise, but on the opposite side, noise helps you pattern because it kicks you out. It starts the patterns earlier. So what happens if you add noise and delays? A whole mix of things. In some systems, the noise helps you. It rejuvenates the patterns. It reproduces them. In others, it makes it worse. I have a paper out there. What's it called? If you want to know about delays in Turing patterns, go look at work by Eamon Gaffney. He did a lot of the early stuff.
Sorry, can you say that name again, and I can write that down?
Yeah, so I'm just trying to find the references, and then I'll put it all in for you. So, Eamon Gaffney. He was one of my supervisors, so that's why he was interested in this. Gene expression time delays and Turing pattern formation systems. So this is the paper where they show everything breaks. This is the paper that breaks everything. Now, where is mine where I show that it's a lot more complicated with stochastic delays? Somewhere. But yeah, so essentially we just did a low simulation because it's very hard to do the analytics. But when we saw what the simulations told us were, there wasn't really even a consistent thread that we could pull out. It was just a very difficult mixed bag. Did a little effects of on delayed. Here we go. This is the one. This is the one. Concentration. I'll put that in the chat. There you go. Yeah, it was just a paper where I just showed we don't know. So yeah, if anyone wants to have a problem, go have a look at that paper. You know, there's a load of problems we still have no idea what's going on.
May I?
Please.
In one of your slides, when you had the boxes looked to me like on the time axis. And I asked myself why there are not boxes coming from the space axis.
Let me
We
go
go
back
to this slide.
So let me. Oh, that's the full presentation. So this was the spatial description.
Well, I don't see the. Okay.
This one at all?
No, actually, no. The one that is doing the temporal, the time, the previous, maybe. There were a lot of blue there, not blue curves like here. Go before, maybe.
One of these?
Yeah, this one, yeah.
Okay.
So along the time axis, I see boxes very clearly.
They're not boxes. They're just where the system changes very quickly.
Yeah, there are time intervals.
Yes.
So the question is, what about space intervals?
Oh, this is discretized in space as well. It's just, you know, I've slammed all the boxes. So if I remember rightly, this started out as 40 boxes and ended up as something like 800 boxes.
So my wrong observation. I have,
but everything is discrete. Everything is discrete at this point. Yes, so we have a time stepping this way and also box stepping this way. Yeah.
Clear. I want to relate.
If you want to see the space, this is what it looks like. It's just I've removed individual boxes and I've slammed them all together.
Oh, that may be interesting to look more closely, but I want to relate to the previous question.
Mm-hmm.
And I have some kind of comment about noise and modeling.
Mm-hmm.
Noise is basically a tool to succeed in the model. And the trouble that I see is that when it is the choice of noise form is successful, it's enough, instead of testing all the other forms of noises. And I'm relating to an issue that I have in other studies, that what is missing is when people use regulation term or penalty, kind of to stabilize or to get the results that they want, they're not relating to the competition between or the effects of noise and regulation term together. So that could be very interesting to look at.
Yeah. Certainly there was, again, around the time of my doctorate, there was a lot of people looking at this stuff in terms of dynamical systems theory, optimal control theory. Trying to, if you have noise in your system, how do you control for that noise to get the output? If you have a very sensitive system and you're doing a chemical reaction or you're doing a physics and your input is noisy, how do you control for that to make sure the output is consistent within error bounds?
Yeah.
So yeah, again, not something I did because as soon as you start talking about applying noise, that's not something I really did. This noise is the intrinsic, so it's being generated by the system itself. I'm not making a specific type of noise. It does whatever it does. When you roll your die, it does whatever it does. To add noise in, you create extrinsic noise, and that's its own field. Although, having said that, I did actually, one of my students did look at this. They looked at what happens when you put different types of noise in. So if you put white noise in, if you put pink noise in, if you put brown noise in, all the noises have different colors. So white noise is when all the frequencies have equal amplitude. Because all the frequencies are there, you get the color white, taking the idea from color theory.
Yeah.
Pink noise is if your frequency spectrum decays like a quadratic, I think. So you have lots of low frequency and very few high. I think that's called a pink noise. And then all the different other colors you can get from playing around with your frequency spectrum. But yeah, he looked into what happens if you put different noise in at the beginning. What does that do to the Turing pattern at the end? Michael Adamar, very good student, really one of these students that surpassed me in his first year. So he's doing some great work.
What's the name?
Michael Adamar. I will find you the, where's the Adamar? This is it, graph facilitated resonant mode counting. There you go. What's the other one as well? There are actually two papers. The second one, the second one is more about the sort of inputs, but the second one is about how you can sort of recast all of this work in mode counting formulation of stochastic interactions. Why is this not pasting? I think it may be too much. Okay, I'll just put that in there. Oh, yeah, can't, it doesn't like that. Why doesn't it like that? I don't know. Having trouble. Ooh. There we go. So that's the name of it.
I found it. I will link it if you want.
It's one of those papers where, although I'm the last author, I was hanging on by my fingertips of what Michael could do. He could fly with this stuff. So I understand what's going on, but how he thought to do it all blew me away. Absolutely brilliant student.
I've added all these papers into the Google Sheet, but if you think of new ones, please do share. I think
yeah. Like I say, I think the best one to start with, if this is a route you want to go into, is the Gillespie one. No doubt there have been later reviews coming. That one was from 2012, I think. And sadly, Dan Gillespie passed away a few years back. But just as a review, it was written by someone who you understood the entirety of the field. So it was written in such a simple way, for such a complex idea to be written so beautifully simple. Absolutely worth reading.
Thank you. Are there any other questions? Well, Thomas, this was great. I hope.
Thank you, Emma. No, I mean, I hope you enjoyed it. I hope I